Hey guys, welcome back to Fire Creek Forge. On this channel, I like to build cool blades, and I focus on the functionality and the utility of the blade, of the knife. And along with that, I want to make something that's aesthetically pleasing and just beautiful. You know, maybe even a piece of artwork if you're so inclined to think that way, and I guess it really is. But you know, this is my passion, and it's also my job. So thanks for coming along, and I'll share this with you here. So I'm starting with a stack of 80 CRV2 steel. That's just 8 pieces here. Got a shipment in here for this particular project, and as luck would have it, my bandsaw blade decided to give up the ghost, and we'll put in a new one here and carry on. This steel is actually quite easy to cut if your equipment is in proper working order, because it comes from the supplier in a spheroidized state, which is a form of annealing, and so it's quite soft for steel and therefore pretty easy to cut. So I'm going to chop off 3 different stacks here, and that's going to be the foundation for the billet that we're going to make for this knife project. Probably should have put that tape on before I turned the saw on, but hey, be careful in the shop. So the next thing we're going to use here is a piece of sawmill blade. It's 15N20, and it lived its previous life in a sawmill in North Idaho, cutting trees into lumber. So got some neat connection there, and it's going to make a great addition to our Bowie knife project today. I need to cut it up into pieces that match the pieces of 80 CRV2 that we just cut. And I kind of goofed up here because I should have gone with 3.5 inch pieces, and I could have used this all the way up to the gullet of the saw teeth there, but I'd already cut my 80 CRV2 at 3 inches because I forgot. So we'll have to figure out how to use that later. Look at that cutoff wheel flex there, yikes. This steel on the saw blade is hardened and tempered for use as a blade, and so I don't have a plasma cutter, so this is the next best thing to cut this into pieces, and it goes pretty quickly with these abrasive cutoff wheels. Now that we have all our pieces cut to the size we need, it's time to clean off each and every surface that's going to be forge welded together. This includes any kind of corrosion, any kind of mill scale, etc. And this is so that these pieces of steel can go together without any kind of inclusions or impediment to the forge weld process. So this is a fairly time and labor intensive part of making a Damascus or pattern welded steel billet. And here I am going back over them again with a rag and acetone, which shouldn't be necessary per se, but that magnet that I'm using has rusty dust on it, which leaves a bunch on, well, too much on the steel as I'm using it. So I want to clean that off as well, because that would be a potential problem in the forge weld. So you know, I find that taking the time to make sure everything is very clean and prepped in a way that you know, precludes any problems down the road, that's really worth it when it comes to building a solid and clean piece of steel to make your blades out of. I'm going to use my arc welder to run a bead down each corner of this billet, and this is simply to hold these pieces of steel together until we can affect that forge weld and turn it into one solid piece of steel. And of course you need some way to hold on to it, so I'm going to weld this bar of mild steel onto the end. And I like to chip off all of the flux and clean all of that crud off as much as possible, because I don't want it in my forge and I don't want it around my tools. It's hard, and it will scratch up or mess up tools, and it can even get into dies and get stuck in there. So clean that up as much as possible. So I like to put my billets in a diesel bath before heating them up. This does several things. First of all, it protects the steel from the atmosphere prior to forging. And if you're going to prep a billet and not forge weld it immediately, it's a really good idea to just dip it or leave it in the diesel, and that will protect it from any kind of atmospheric conditions that can and will create rust or oxidization between your layers, which is not good. And besides that, or beyond that, when it does burn off in the forge, it leaves a thin film of carbon deposit, which helps protect the steel a little bit still, and then also provides a small carbon deposit which aids in the forge welding process. And then finally, of course, the flux, which cleans and protects the steel even further. And once we've packed the billet a little bit and then brought it up to final forge welding heat, we can go ahead and complete the forge weld in the press here, as you can see. And you notice that I didn't put the whole thing under the dies and just press straight down, but I worked it from end to end, and that allows any flux or impurities to be forced out the other end as you work it forward or backward, as the case may be, and help preclude any inclusions or pockets that could potentially form if you just press straight down immediately. There's a few pieces of steel that are kind of proud off the side here, and when I go to forge it on the bias, I don't want to fold those over and create a cold shut in my billet. So I'm going to grind those off clean and then proceed with forging or working the billet down. You can see the iron oxide or forge scale break apart as that billet changes shape. This is where the forging press really shines. It works well for large cross sections of steel that can hold the heat for a longer period of time. And we'll work this billet down to about 1 inch thick, and the thinner you get, the less efficient or effective the forging press becomes. But it is definitely a very useful tool for forging these large billets. So there we have it. It's down to, like I say, about 1 inch thick, and the main thing I'm looking for here is the length that I need to cut it up into the pieces I need to restack and re-weld it for the desired layer count. So we started with about 41 layers, not counting the ends that are going to be back up against each other. And in this case, I had a little more of a cruddy end than normal, so I had to cut off more of that. But I'm going to save that, and I can use that in a future project. So I need to cut this up into 5 pieces, and there we go. That's going to give me just over 200 layers, which I find is a really good layer count for most knives. It allows you to see the pattern still when you're starting with about 1/8 inch thick material, and just provides a good solid billet. That's what I like to do most of the time, between 200 and 300 layers. So once again, we do have to clean off all the surfaces that are going to be forge welded together again. And I'm starting with the angle grinder because this forge scale is extremely destructive to even high quality grinding belts. So once that's cleaned off, we can go to the grinder and give ourselves a nice flat, clean surface to mate to the next piece of steel. So repeating the processes that you just saw, we'll go ahead and forge weld this together again. And again, I'm working from back to front to give the opportunity for any flux or impurities to squeeze out from between the layers and bring that steel together into one solid piece. So getting this billet worked down here. And I'm going to use a portion of this billet for other projects. And so I don't need to forge down the whole billet to our thickness for this Bowie knife project. So I'll just do this on the front part here. And I'm looking for a little over 3/8 of an inch thick. My center piece, or the center steel for this blade, also 80 CRB2, is just over 3/8 inch thick. But I want my Damascus cladding pieces to be a little thicker than that, because I still have to grind off the forge scale and get a clean surface to, again, forge weld those pieces together. And then on the final process or final finish of the knife, I'm going to have to grind off the outer layer to finish the blade. So the end result should be pretty equal amounts of steel across those three different pieces in our Sanmai construction. So again, being meticulous, and the steel's a little hot here to handle, but making sure everything is clean and ready to go. So far the knife build is going pretty smoothly. You know, these are all time consuming and sometimes labor intensive steps, but the end result is worth it. So again, we're going to tack these together so we can forge weld them. And I'll use another piece of mild steel as a handle. In this case, I went ahead and cut the center piece of steel a little bit longer so it could hang off the back of the billet and hopefully keep the arc weld there from interfering with our forge weld on our Sanmai billet. You'll notice that the billet here is just a red heat, not even quite, and I want to put flux on there as quickly as possible. It's not able to fully melt it yet, but getting that on there as soon as possible is best in my opinion. You can see how that opened up there, but because there was flux on those surfaces and I was working it from front to back to squeeze out that flux and impurities, we got that almost completely closed up and welded. Just a little spot there that I had to readdress, and we're getting it closed up right there. So that gives you an idea of why we do things the way we do. So we have our Sanmai forge welded together, and now it's time to work this into a blade. So I went so far in the forging press, and up to now the 50-pound little giant has been left out and is probably crying in the corner. But this is where the power hammer begins to shine. Once you get down to those thinner cross sections, and we're still probably about 7/16 of an inch, I think, maybe half an inch. And the power hammer allows you to work the steel longer because it does not suck out the heat the same way that the forging press does. But the power hammer is limited in the size of cross section that it can effectively work. So that's why having these variety of tools is very beneficial if you're doing this kind of thing all the time. I want to work my billet equally on both sides as much as possible, and that will help the center steel stay centered so that when we go to finish and grind our blade, we have equal reveal on each side of the blade instead of having things off center. The tang for the handle on this blade is tapered a little bit, and using my straight peen hammer to spread that out a touch. And here I'm starting to forge in the bevel, which I'm going to do not as far as I would on a regular mono steel knife, but I do want to forge it in somewhat. That's going to minimize the amount of grinding, but also it's going to bring the Damascus cladding on our finished blade down closer to the edge. And in the traditional application where the Sanmai cladding was a low carbon steel, that would provide strength to the, or toughness I should say, to the knife further down closer to the edge, which is a desirable characteristic. We don't really have to worry about that in this case, but this is a better way to do Sanmai in my opinion. So we need to continue thinning the blade down. That's going to give me my length that I need as I continue to work this down. Here, as we near the finished forge dimensions, we're still at about a 1/4 inch thick on the edge here. And I'm using my straight peen hammer to forge in wavy lines, for lack of a better term, and that's going to create more of a pattern in the Damascus cladding on the finished blade. As we progress closer to the finished dimensions and forging in that bevel just a bit more, I'm using my regular rounding hammer, trying to get everything uniform and straight. Again, using my straight peen hammer to spread out or widen the handle and ricasso area a little bit, and then we'll flatten that out on the power hammer. So there we have it. We still have plenty of steel everywhere, which is good, because we're going to leave a lot of that until after the heat treating process is complete. Oh, but I forgot. I actually, as I was checking my final straightening, I realized that my bevel was a little bit off center, and normally it wouldn't be really enough to worry about too much. You could correct it with grinding in the final project and not even have a problem. But in this case, because we're doing a San Mai construction, we need to make sure that we forged it as close to center as possible, so that when we go to finish our blade, we don't have an offset or out of center edge steel giving us an uneven reveal on each side of the blade. So that's important. So you saw me pulling out of the forge there at a dull or low red heat, almost not visible. And what I was doing there was I just heated it up to a dull red and let it sit there for a little while. And that's just a quick, simple spheroidizing process on the tang there, which is going to allow us to get our bolt holes drilled in the handle without issue. So I'm going to grind off some of the excess and rough in the finger grooves on this knife here. There's still going to be quite a bit of grinding to do, but in my opinion, why do any more grinding on a hardened blade than necessary? So it's time to put in our holes for our handle bolts. And this is a scribe that I built a long time ago, but I also use it for a center punch, and it works pretty well for that too. So you can see how that steel is pretty soft, which indicates that our little spheroidizing process was successful. And again, the drill bit here is cutting no problem, and it's not really the sharpest drill bit out there, so it works out pretty good. Now we can go ahead and begin our normalizing and thermocycling process. The first cycle here at 1600 degrees, and I'll let it soak for about 15 minutes. Take it out, let it air cool in still air. That's going to reset the grain structure, the grain size of the steel, and relieve a lot of stress that we've created in the forging process. These are very important aspects to heat treating the knife. And once we've done that, there's multiple more thermocycles that we'll go through to further refine the size, bring the size of the grain down. That is one good thing about ADCRV2, is that with the vanadium content and the chromium content, but it really helps keep that grain size from getting too large, even at the high forging or forge welding temperatures that are necessary to this type of build. But refining that down with the thermocycles is going to give us a high quality, high functioning blade with this steel that we're working with. So I'm using a quick ferric chloride etch. It's kind of wore out, it's not doing so good, but it's just enough to tell me where my edge steel is, and then I can adjust my grind accordingly so that we're on track to where we need to be on the finished grind of the blade. And then I can go ahead and harden it. So you saw me rough grind the blade. That's not absolutely necessary, but again, why grind hardened steel any more than I have to? And that also helps me make sure that my San Mai is centered. So now we have a nice hardened blade, and we can go ahead, make sure that it's straight, and get it tempered. Okay, so here we are the next morning, and the knife is fully tempered twice for 2 hours each time, actually. And now we are ready to do the finish grind on this blade. And we still have quite a bit of material to remove, even though we did a rough grind on it here. And on any pattern welded steel or Damascus steel blade that you do, in general, you're always going to want to remove the outer layer of the steel everywhere on the blade. And that's because you want to finish that surface to an appropriate level that you can then etch in your ferric chloride or acid, depending on what you're using, and reveal the pattern. So as I'm doing the finish grind here, I have it back and forth in this old ferric chloride here, simply to show me where the center steel is. And this one gave me a little more trouble than I would have liked, but just keeping track of where that steel is, because you're unlike a normal forged or even stock removal blade, where you can look at the outside of the blade of the steel and say this is where I want my angles, etc. You have to grind your bevels to an invisible point, an invisible reference point. And if you want your blade, your edge steel to be centered in your blade, which of course we do. But anyway, at this point I've got it finished ground, and I'm really liking the appearance of the blade at this point. Very clean welds, very clean piece of steel, solid, no inclusions, no voids, no anything at all. Just what you're seeing there appears to be a solid mono steel. It is solid, but it appears to be just originally one piece of steel, which is what you want. So now that we've got it finished ground, it only went down to 120 grit because I would normally go to 220, but I don't have any 220 belts at this point. So we're going to start hand sanding, and the first grit I'm going to use here on the sandpaper is a 220 grit. And this is laborious and time consuming, and I won't show you the several hours that it took me to hand sand this, or at least a couple hours, but you get the idea of what's going on there. So after I've got it sanded to 220 grit, I went ahead and put a small shoulder at the top of the tang, where the guard is going to butt up against, as it does down at the bottom near the finger groove or the finger cutout. And I could have done this before quenching, before heat treating and all of that. It does create a potential stress riser. That's not why I didn't do it. I just didn't think of it really. So that's actually going to put my bolt holes a little off center, but I still need to bring the grip down a little bit. So I'm going to cut in those finger grooves a little bit more, and that's going to affect the proper orientation or indexing of the bolt holes. So now that I have this blade finished sanded or hand sanded down to or up to 800 grit, I'm ready to go ahead and etch this blade finally. This is great because I'm excited to see what the pattern looks like, and at this point there's been a lot of work gone into this blade, so it's good to reach this milestone here. So like I said, 800 grit, clean it off with acetone, and into the ferric chloride it goes. You'll notice that it's a fairly weak solution of ferric chloride. That PVC or black pipe tube is almost full of water, up to within 4 inches of the top, I believe, and I probably raised the level about 2 inches with the ferric chloride. So not a super heavy concentration, and that's what you want. You don't want your ferric chloride so strong as to attack the nickel content steel to the same degree as the carbon steel. If this happens, it will be very difficult to achieve a deep, crisp, and high contrast etch on your blade. Now that we have the blade ready to go for the most part, we can begin working on fitting the guard. And I've got a piece of 3/8 inch thick brass here, inch wide, to build this guard out of. And this is to client specifications, so we're going to build a nice hefty very serviceable guard for this big knife here. And I'll start by drilling holes out and then connecting them with my Dremel tool and a carbide burr there. And using the tip of that burr works really the best instead of putting it all the way through in there. And then some file work, and we'll go ahead and start fitting this. And the tang is tapered, if you recall, so that's going to aid in a good fit here. So basically it's just a matter of trying it and removing a little bit of material from the slot and then trying it again. And you want it to be a tight fit, or at least I prefer to have a fit that you have to drive on slightly, but not to the extent that you start deforming things and create a really tight, overly tight fit. So snug, I guess, is the word. Once I got it fit on there, I hammered on the sides a little bit to tighten the slot up just a touch, and now I'm cleaning up those hammer marks and thinning the guard down just a little bit, getting things squared up. And the design of this guard is tapered a little bit on the ends, and so we'll go ahead and grind that in at this point. So at this point we've got the guard almost completely finished, and I'm using a brass bumper or spacer for installing it at every point, or every time at this point, because I don't want to mar up the brass. So a pretty decent fit there on the front. But I kind of goofed up on the back here. I forgot that I had some reveal on both ends there, and I kind of wallowed that out a little more than I should have with the Dremel tool. So I'm showing you how to fix that. We still have plenty of material on this guard, so we're going to use the ball peen hammer to move some of that material over, and then we'll clean up the surfaces again here. And the result is pretty decent. As you can see there, we've got it closed up pretty nicely. So now we're going to go ahead and fit the desert ironwood handle scales, and I didn't film the part where I fit the angle between the guard and the ends of the scales, and that's just a matter of putting them up in there, checking to see if any light shows through, and then using the emery cloth on the granite block to sand it to the appropriate angle so it fits perfectly up against the corner of the guard and the tang. Then we can clamp these scales to the tang and drill the holes exactly where they need to be, and then go ahead and countersink out the holes for our loveless bolts. Loveless bolts were developed by a knife maker named Bob Loveless, hence the name, but they're a very versatile and very strong method of attaching handle scales to a full tang knife. So now we're faced with the task of finishing the ends of the tang right up close to where they're going to be by the guard. In this case, we can't finish the guard and the tang together because of the pre-ground angles on the guard and the way that the scales come away from it. So we're going to have to finish everything up close to the guard prior to installing it so we don't ruin the guard. And I'm just going to use the belt grinder to carefully chamfer things. I kind of marked stuff a little bit there, like you saw, and it's sort of a rough estimate of where the scales need to taper to, and this is what it looks like roughed out. So then using some sandpaper and cleaning it up there, we'll get it ready to install up against the guard. And this is the first fit up, so a little bit more refining, and we'll be good to go. Alright, this is the final assembly here for the last time, using epoxy in everything, in between everything, making this a nice permanent solid build there. Once the epoxy is cured, we can go ahead and start shaping the handle, which starts with grinding down the excess material and getting the loveless bolts down to the level they need to be. So we just start revealing the nuts on that assembly. Grinding in the finger grooves here, and there's a lot of contours on this handle, so Started with the small wheel and continuing on with a half round file, and then of course sandpaper, and just working my way up and getting everything finished. Finally got it sanded up to 600 grit. We'll go ahead and put some Watco oil on there. That really brings that grain out on that desert ironwood, so looking really good. Alright guys, we're just about ready for photos of the final product here. I just have to put an edge on, clean off the stickies, and I'll get some pictures up here, so stay tuned. I'm really happy with the way it turned out overall. It feels really good in the hand. It's going to be a good knife. I'm excited to get it off to my client as soon as I get a sheath made for it. But if you've enjoyed the video, found it interesting, educational, or both, consider supporting the channel. A couple different ways to do that. Hit the like button, leave a comment, leave a question. Doesn't cost you anything. If you want to go a step further, then you can support on Patreon. Link is down below. And last but not least, go to my website, check out the knives that I have up there for sale. I'm always adding new ones, so different ways to go about that. As always, thank you for watching, and we will see you on the next video.